Okay, this is my final project on segmentation of the left ventricle, and I'm a solo team. So a little background on the problem. It uses echocardiograms, which are pictures of the heart that are created with sound waves, so ultrasounds. And viewing these echocardiograms, it's important to identify the left ventricle because that's the heart's main pumping chamber. And so deep learning methods are trying to annotate that. And the goal of this project is to implement a segmenting problem and then use that segmentation to predict the volume of the left ventricle, which can then predict the percentage of blood leaving the heart each time it contracts, which can diagnose certain heart failure. So these are a couple of things that are already going on. So Echo RCNN is based off of a mask RCNN and RetinaNet segmentation. And this process is semi-supervised because the first frame has to be annotated before beginning. This method finds the volume of the left ventricle, but they don't go into detail about how. The EchoNet dynamic is they publicly released a data set of about it's 10,030 annotated echocardiograms, which significantly promoted the research on this because one of the main issues with conducting this research on the chamber segmentation was that there was a lack of public data sets. And so EchoNet Dynamics has that, and they publicly released it. And they use CNN architecture, and they use spatiotemporal convolution, which is new to medical imaging because, like I said, there isn't a large amount of medical videos that are labeled. So my method is based on a Kaggle user named DPAI because I needed guidance on how to extract the end diastolic and end systolic frames because it was a video. And so that helped me extract those frames, and the ES frame is when the left ventricle is the smallest, and then the ED frame is when the left ventricle is the largest. And I also really liked the way that he displayed the results, and so that is a picture on the bottom of an example of how the results were displayed. The data set I'm using is the EchoNet data set that I mentioned in the last slide, which is easily accessible through Kaggle. And the model I'm using is the MobileNet V2, which is a CNN that is 53 layers deep. And during this time, 48 key points are identified. Oh, I'm sorry, it's 84 key points that are identified. And they're displayed in this example. So the first 4 data points are the longer axis, which you can see in the middle. And then the next 80 are the data points that are going from left to right. And this is the resulting image. And the resulting image inspired the means that I'm going to talk about later of how I want to calculate the volume of the left ventricle. These are just some of the results. This is the learning curve. So as you can see, the chance for false predictions significantly lowers after each time. This is a visual of the predicted versus ground truths from an ED frame. And these are visuals of predicted versus ground truth on ES frames. As you can see, the predictions are not as accurate compared to the ground truth. This is the case for many of the ES frames because the left ventricle is so small. In this visualization, you can see that the prediction didn't accurately predict the curve towards the bottom left. And I see this in multiple cases when the curve is more dramatic than the norm, I suppose you could say. So after doing all of those predictions, the volume calculation comes into effect. And so normally left ventricle volume is calculated using the disk method. So each of those horizontal key point bars that you saw right here will be measured, and it will be used as the diameter, and then the area of the disk is calculated and summed. And then that's multiplied by the height of the full thing. And so basically you're viewing the left ventricle as kind of like a 20-tiered cake, which is not accurate of real life, how the ventricle is shaped. So for my method, looking at this, I visualize sort of like a continuous function on each side of the axis. And I'm still working on programming that full aspect of the project, but I plotted the key points from the left and the right, and I made 2 curves. And I'm going to integrate those functions to find the area under each of those curves, and then revolve both of them around the middle axis and divide it in half. And I think this will better model the actual shape of our heart chambers because they're curved and not like a tiered cake. And it will also be more sensitive to the curvatures that are sometimes only on one side and not both. Some of the issues that I ran into is that due to the size of the data set and the computation that comes into effect, it takes a decent amount of time to run. And so when I'm trying to edit the code, I have to make sure that I edit a lot of the code or like everything that I want to before running it, because it will take a long time if I only do piece by piece. So, and then also the ground truth volume for the data set that I'm using is based off of the disk method. So it's sort of not a great comparison with the means that I'm trying to figure out the volume, but I hope that this will help the fact that the curvatures aren't always getting predicted correctly. And so it'll be more sensitive to those curves and maybe become more accurate. I'm still working on the code, so I'm not exactly sure how that's going to turn out. And this is the Kaggle dataset that I use, and then the visualization from the DPAI user, if anyone wants to check it out. And that's it. Thank you.
Okay.